Sometimes we oversimplify things and we say, there's only three states of matter. Well, there's actually plasma, there's non-Newtonian solids, there's all kinds of states of matter. We're going to focus on the big three. We're going to start with solids. Solids are much denser and they're more tightly packed. The particles are vibrating. So even though they're locked together, they're still moving. So a solid still has some level of vibration if it's at some temperature. Remember, the only way that motion can stop is if we reach 0 Kelvin. They have a definite shape, a definite volume. We can measure both with certainty. They also have the lowest amount of kinetic energy. Kinetic energy is the energy of motion. So these particles are not very energetic. They're not moving very quickly because temperature is a measure of the average kinetic energy of a substance. Liquids are also fairly dense, but they're loosely packed. The particles are flowing, which means they move, but they're still kind of stuck together. There's some kind of a force of attraction holding them together. They have an indefinite shape, but a definite volume. What does that mean? Okay, let's heat up this solid a little bit. Okay, it starts to move around a little bit more, and you can start to see that it loses its shape. However, we put this liquid into a container, we can still measure its volume. We can still measure it in a graduated cylinder. So its shape does not stay maintained, but its volume can be measured in a container. It has an intermediate amount of kinetic energy, like it's moving a little bit more, but it's not quite as energetic as the gaseous state. And you can start to see some particles escaping into the gaseous phase already. A gas is extremely low density, large amounts of space in between the particles. They've been separated to such an extent that there's really no force of attraction between those particles. And I'm going to keep heating up this liquid until it entirely becomes a gas. The gas particles move around rapidly, randomly. They collide with the walls of the container. They collide with each other. It's like a bunch of kids at recess, right? They're bouncing around. And the kinetic energy of a gas is the highest out of all of the states of matter. It's the most energetic. However, the shape and the volume of this gas are both indefinite. What does that mean? Well, if I take this gas and I poke a hole in the container, it's going to escape. It's going to move to a new place. It's not going to stay in one spot. So the shape of a gas is ever changing, and its volume cannot be really measured with much certainty because it could change. Indefinite shape, indefinite volume. Phase changes are what we just observed. When something goes from one state of matter to another, sometimes it can skip a state of matter in the process. Usually, there is an energy change accompanied with that. If I go from a solid to a liquid, liquid particles are moving with greater kinetic energy than gas particles, so I'm adding energy to make that happen. If I go the reverse way from a gas to a liquid, I've lost that kinetic energy and I release energy, and the same holds true when I freeze. Phase changes are always physical changes because they don't change the chemical composition of the substance. This chart summarizes the 6 main phase changes that you need to know. You need to know which ones are endothermic, which means heat absorbing. To go from the solid to the liquid phase, melting, takes energy. Vaporization is when a liquid goes into the gaseous phase. Vaporization is the best word to use because evaporating and boiling are types of vaporization. But vaporization kind of encompasses all of those terms. You can also skip the liquid phase and go straight to the gaseous phase. That's called sublimation. And all 3 of those phase changes require energy because it takes a less energetic state of matter and puts it into a higher energy state. Exothermic phase changes are ones in which we're losing energy, such as condensation. Oh, those gas particles had a ton of energy. Well, now they don't as a liquid. And when a liquid freezes into a solid, oh, it lost all that energy, so therefore it loses energy to the surroundings. The opposite of sublimation is deposition, which also can occur from the gaseous phase to the solid phase. You should also know the difference between a gas and a vapor. Two very similar words, but slightly different. Under normal conditions, and we say normal temperature, normal pressure, atmospheric pressure, room temperature, a gas is something that just exists as a gas and nothing else. So like helium in a balloon, that's a gas. Water, on the other hand, you leave a puddle of water sit out in the sun, it's going to slowly evaporate. And why is that? Well, it's a vapor. So under normal conditions, water is a liquid, but some of it can evaporate and form steam above the surface of the liquid, and we call that a vapor. So two very subtly different but somewhat similar terms we use when we describe gases versus vapors. When we describe matter, matter can be separated into two categories: pure substances and mixtures. The primary distinction between these two is that a pure substance cannot be separated by physical change, while a mixture can. And when we talk about pure substances and mixtures, pure substances really are composed of two things: elements and compounds. When we mix elements and compounds together, but not chemically, just physically, we can create a mixture. Pure substances have a uniform chemical composition. All atoms of neon are the same if you have neon gas in a tube. Or if you have water, water is a compound, it's a pure substance, right? Water is made up of two atoms of H and one atom of O, uniform chemical composition. Mixtures are not. Starting with the next mini lecture, we're going to talk about some more distinct differences between pure substances and mixtures and how we start to classify them into subcategories.